Great. Well, let's continue. It's great to have Srinivas from University of Buffalo to speak about tile coverings. Thank you.
I'd like to start by thanking the organizers for giving me this opportunity to speak. The talk is a report on some joint work with Elaine Esnault over a few years, and we still haven't fully solved the problems which we were thinking about, so I want to also report on what those questions are and how far we've got, and maybe somebody from the audience might have suggestions of how to proceed further. Some parts of the works have involved other people, Lars Kindler, Kai Rulin, Mark Schusterman, Jacob Stix, Marcin Lara. And then, of course, other people we talked to informally, but these are co-authors and parts of the book. So I'm interested here in finiteness questions and boundedness properties of certain quotients of the so-called étale fundamental group of a variety, of an algebraic variety, over an algebraically closed field of positive characteristics. This is the background, the type of question I'm studying. So let X be a connected variety over an algebraically closed field K, right now of any characteristic. K could be the complex numbers at the moment. And let pi1 étale X be the algebraic fundamental group of X. Strictly speaking, you should have a base point, but I'm going to suppress it for various reasons. For simplicity, it's not so important for my kinds of questions. By definition, this is a profinite topological group with the property that the finite quotients from pi1x to a finite group G correspond exactly to the connected finite Galois étale covering Y to X with the Galois group G. So you have the collection of these coverings and sort of you assemble them into a kind of tower, and that produces this étale fundamental group. And therefore, the étale fundamental group is realized as a certain quotient of the Galois group of the field of rational functions Kx of the variety X. So, of course, you have a covering Y to X, you have a corresponding extension of function fields, and that's also a Galois extension of the same group G. But the ones, the Galois extensions of the function field which come from a global thing are restricted, and so you get a quotient of the Galois. Now, if K is the complex number, then from something which people call the generalized Riemann existence theorem, we know there's a natural group homomorphism from the topological fundamental group of the corresponding complex space to this étale fundamental group, so that the induced homomorphism on profinite completions is an isomorphism of profinite groups. So I get some theorem about the structure of this group as coming from topology. So for example, you can use this to compute Galois groups using topology in various situations, which people purely working in algebra are a little surprised to see sometimes. Anyway, topological fundamental group is a finitely presented discrete group, which means you can write it as a quotient F mod R. F is a free group on a finite set. R is a normal subgroup of F generated by a finite set of elements put together with the conjugates. And there are the topological fundamental group of complex algebraic varieties have been studied extensively. For example, Zariski was one of the people who studied it long ago. And in the 1920s, there's a paper of Zariski talking about the Poincaré group and trying to prove Lefschetz type theorems for the Poincaré group. So that's one of the early things. And then Zariski has many other things related to pi1 and many other mathematicians, but I wanted to mention Zariski specifically. On the other hand, in algebraic geometry, we have this ground field K. So suppose K is some field of characteristic 0, and I can embed K in the complex numbers. Then Grothendieck showed that the étale fundamental group of the complex variety and the étale fundamental group of this X over the given field K are canonically isomorphic. So the study in characteristic 0 pretty much is influenced by what comes from topology, and I get these group theoretic properties of pi 1 étale X. It is finitely presented as a profinite group, and for example, one of the theorems of Zariski implies that if X is a normal quasi-projective variety of dimension at least 2, you could find an irreducible curve inside X, which is in fact non-singular, such that the map from the étale fundamental group of the curve to the étale fundamental group of X is surjective. In fact, Zariski would say the topological fundamental group is surjective, then by passing to profinite completion, étale is also surjective. So these are theorems over C. So the question I want to sort of discuss in broad terms is to what extent can we extend the characteristic 0 results to characteristic P? Are they valid, and if not valid, how can we correct them, and what types of things might be right? That's the background of this project. And for simplicity, perhaps I should stick to non-singular varieties for the most part. There are also already enough problems there where we don't understand what to do, and putting in singularities makes your life even more difficult. So let's not do that right away would be the thing. Okay. So I listed here two properties, finitely presented and the existence of this curve. You might call it a kind of Lefschetz curve. Both those properties fail immediately in characteristic P for non-proper varieties, for affine varieties, for example, because of the presence of what's called wild ramification at the boundary. So let me briefly give a couple of examples for non-experts or those who are not familiar with characteristic P. One statement about finite generation is false for the following reason. If this group was finitely presented, then you make it abelian, tensor with Z mod P, you would have to get a finite group. And this, the dual Z mod P vector space of this is the first étale cohomology with Z mod P coefficients, and this is not a finite group. It's not a finite dimensional vector space over Fp. From Artin-Schreier theory, there's a formula for this thing. It's the co-kernel of this map of Fp vector spaces. Take the coordinate ring of A1, the polynomial algebra in one variable, take the map from it to itself, given by sending a function f to f raised to p minus f, and take the co-kernel. And it's easy to see, for example, if you take homogeneous linear polynomials, that maps injectively to the quotient. K, my ground field K is algebraically closed, that's already an infinite dimensional subspace in that quotient. And of course, there are lots of more stuff there. So it's far from being a finite group. So therefore, this is far from being finitely general. This is, I mean, it fails in many more spectacular ways, but this is one obvious way. What about the other thing, about the existence of a curve inside a higher dimensional variety? That's also completely wrong. If you take X equals spec A, a connected affine variety of dimension bigger than 1, D, any Zariski closed set which is a proper subset of X, I claim the map from the étale fundamental group of D to the étale fundamental group of X is never surjective for any D. And this is also for essentially trivial reasons in characteristic P. Again, let me look at the induced map the other way on abelianized étale fundamental groups tensor Z mod P. In other words, let's look at the map on étale cohomology from H1X Z mod P to H1D Z mod P, the natural map. I'll just take these Artin-Schreier covers of X, which are the things which I'd get here. Those are things of the form T raised to P minus T equals F. Those coverings, I have to choose functions F on the space X. So just to choose a function in the ideal of D. So when you restrict this covering to the subvariety D, that means I'll have to take the function F restricted to D and then take the same equation. But then it's the equation T raised to P minus T equals 0. That's the trivial covering space. So that's the 0 element in étale cohomology. So anything here in the ideal of D will automatically give 0 here. So all I have to convince myself is that it's possible to write down things in the ideal. Once it's a non-trivial ideal, there are elements where the corresponding covering is non-trivial on X. That's an easy exercise. Just take something whose zeros are not reduced, let's say. are reduced, sorry, don't have a non-reduced point, for example, that would be a way to do it. Outside D. Right. So how do we repair this? The way to understand these bad phenomena, one way is to think of a compactification of your space X and then try to understand what happens along the boundary, and in terms of that boundary data, try to say something more reasonable than just saying everything is wrong. You want to say something is right? That's the whole point. So one obvious setting is the following. Take a non-singular variety. I can talk about a good compactification of this non-singular variety if there's a proper variety x bar, which is also non-singular. It contains x as a Zariski dense open, and the boundary is a divisor with simple normal crossings. We don't always know such a thing exists, by the way, in characteristic phi, but let's believe that, or let's take that situation where it does happen. At least that should be a better situation than the generic one, even if whatever. Let's try to understand that situation better. That would be the first step. Elena Schusterman and I obtained the following result in 2022, that X be a smooth variety over an algebraically closed field of characteristic P. Assume X admits a good compactification, which is also projective. It's not clear projective is required to get good properties of the fundamental group, but our analysis uses it. In that case, we can prove that something called the tame fundamental group of the open variety X is finitely presented as a pro-finite group. And in particular, if there's no boundary, if X itself is smooth and projective, the et al. Fundamental group is finitely presented. Now, it may not be clear. In fact, earlier when I've given this talk somewhere, very politely, one or two people have asked me, I suppose the smooth projective case is there in SGA and you guys have done something where there's a boundary. No. In fact, there is no, let's take curves where you assume you understand everything about the fundamental group. I believe there's no example of a curve of genus, at least two, for which you can write down a presentation of the et al. Fundamental group. Okay, maybe some people sitting in the audience look challenged. Maybe one of you guys will produce such an example. It would be very nice. But there are no examples. It's impossible to compute a presentation of anything. So whatever you're doing here has to be by some indirect method. Since you can't compute any examples, that seems to be, at least nobody knows how to compute any examples at present. I'm not even sure we know how many relations to expect. Is there a conjecture about that or a formula? Even for smooth projective curves of dimension of genus at least 2. K is an algebraically closed field for me. I'm thinking only of geometry, really. You're saying K equal to FP bar versus the, no, it doesn't. Okay. Yes, that is true. That there are theorems of that kind saying that the fundamental group actually changes. If you have a non-trivial specialization, the et al. Fundamental group actually changes. There are theorems of that kind, coming from the Annabelian people, which is how they get finiteness theorems for certain Annabelian, using that. Yeah. Right. It's those people who tell me that basically it's going to be impossible to write a presentation. So I believe that. So, but anyway, the theorem is that it is finally presented, though I have no idea what the presentation looks like. Okay, as a corollary, once you can do the smooth projective case, some things you can do for general X by general algebraic geometry descent method. This was worked out by Lara and myself and Sticks. A paper appeared recently, that the et al. Fundamental group of a proper variety of an algebraically closed field is also finitely presented. And here you use an alteration in the sense of Dion. The altered thing is very nice, smooth projective. There you know everything. And maybe you have several, you have an alteration is a disjoint union of pieces which you have to glue in some fashion. But the contributions to the fundamental group coming from such gluings are somehow like combinatorially defined. There's a kind of Van Kampen type story, and that Van Kampen type argument is there already in SGA. So you can use that machine, and using that you can deduce the general case from the smooth projective case. There's some work to do, but not. It's more or less a corollary, I would say, of the other work. Okay. One ingredient in our proof, which I thought I should highlight here, people here, certainly arithmetic geometers were earlier not familiar with this, is the theorem of Lubotsky from group theory, which says that if gamma is finitely generated profinite, then to check it's finitely presented, there's a criterion in terms of cohomology. There must be a constant such that if you take any finite dimensional representation of gamma over some prime field in any possible characteristic, so you have to consider all possible L, compute the second cohomology of this gamma acting on M, which will also be a vector space over the same field, take the dimension, that should be bounded by constant times the dimension of the underlying representation. If there is such a constant, then the group is finitely present. And the constant, so to speak, you might think of one constant for each prime L, and then there must be a uniform constant for all, including L equal to P. Including L equal to P, which is the characteristic. So, of course, there are different types of, you can imagine different types of arguments in one. Independence of L type questions and things like that are behind here. Okay. Right. Sorry, I'm going the wrong way. And I must say that this Lubotsky thing is 2001. I didn't know about it. Elaine brought this to my attention, and some of that was an important input for us. And recently, I'm in some journals and so on, you see things coming across the editorial. Some other arithmetic geometers, some number fields have started using it and are getting various things. So people are slowly becoming aware. That's why I wanted to highlight this thing. If you need to prove finite presentation for something coming in arithmetic geometry, this might be a good tool to know.
Does it fail if you remove prime?
Sorry?
If you remove prime?
No, you could say for any finite module M. But then you'll have to, instead of taking the dimension, you'll have to take log of the cardinality or something. But it's, but then you reduce the question for general finite modules to the one prime at a time by Chinese remainder theorem or something. Yeah. So you might as well formulate it like this. Right. Now, okay, so we have some idea if there's no boundary, things are not so bad. Some things are true, analogous to what we got over complex numbers, not in the same shape, but the final statements don't look so different. So now let's try to take a case where you have a boundary and try to understand better whether we can try and say something. Okay. So what you would like to do in principle is suppose you have an étale covering y to x of some non-proper, but let's say quasi-projective variety, and let's assume that we have a compactification x contained x bar, which is projective and at least normal, non-singular would be even better. Then you would of course have a corresponding branch covering y bar from y bar to x bar, where y bar is sort of the normalization of this x bar in that function field extension. Of course, it depends on the compactification. So in the end, if you set up some theory, you may like to know in the end how do things, but that's too, we're not yet at the point we should be trying to think about those things. We understand don't understand enough probably at this point. So let's just take one and try to see what I can do with it. And then what I'd like to do, I'd like to put some restriction on the possible wild ramification along the boundary. Wild ramification are just some words right now. There are no mathematical content yet, right? I mean, I've not given any content to it in my talk. So I want to first try and understand a little better. Can I quantify what it means by wild ramification at the boundary? So then using that quantification, bound it in some fashion, and then try to go back to the cover. So how do we quantify this wild ramification? There are different ways to try and do it. There are many quite difficult technical ways. I don't want to get into those things. I'm not an expert really on that. So if you have one of these things and we extend this, so let's take a map of curves first. So let's start with a finite Galois étale morphism of non-singular curves. There I know how to compactify. There's a standard way, only one way to do it. There's no choice. And the structure at the boundary is not so complicated, right? At the level of Galois theory, I could think of the local behavior at the boundary as corresponding to something like this. Some extension of fields like this, Laurent series fields like this, and this is a finite Galois extension with group G, where G is the local Galois group of some kind at a point. Right, so one knows that if you have such a finite Galois extension, it always has the following structure. 1 goes to P, goes to G, goes to Z mod MZ, goes to 1, where P doesn't divide M, and this is a P group. Now, the local Galois group there is always known to have a unique P-Silo subgroup, because we're in characteristic P and we're looking at extensions of this type. If we were in characteristic 0, the only possibility for such an extension would be to take the nth root of the parameter or some n up to change of variables. In characteristic P, the structure is of course more complicated because the ground field is characteristic P. So then you get this. So, but it's not at the level of group theory, it doesn't look so bad, right? But the problem is there are lots of finite groups G which operate on this, and the structure of the automorphisms of K power series U over in positive characteristic is very complicated. So take any such complicated finite group, take the invariants, that's another thing, and then you can think of it as a covering, and then from the ground, if you look up, it looks very difficult to follow. Anyway, that's sort of the business. But from this structure, there is more fine structure of the group P from ramification theory, so-called higher ramification theory. You have the lower numbering, upper numbering, there are all sorts of tricky things. Let me not get into all that. If I try to do it here, I'm sure to write down wrong, make mistakes. Let's just get what we get out of it as a black box. I can associate, I claim, to any point in the boundary a non-negative integer nx. So I've got a point x in the boundary where I might have ramification, I might have a non-trivial local extension, and then associated to that data, I claim that there's a way to associate a non-negative integer, nx, and I'll call it the Swan conductor of the map at the point. So, since I haven't given you the detailed description here, and I haven't told you a rigorous definition of Swan conductor, but let me instead just say that it can be defined using this so-called upper numbering of this local Galois group, which is some complicated thing. And I don't want to get into the details, but I'll try to tell you some properties of this Swan conductor. One is that this number is 0 if and only if that map is actually tamely ramified over the point x. That's the situation where there's no P here basically. There's only the Z mod. So that looks like characteristic 0. Secondly, if I want to compute the difference between the Euler or compare the Euler characteristics of the covering and of the base, and I look at compactly supported Euler characteristic, well, in characteristic 0, I would say Euler characteristic multiplies in a covering by the degree of the covering. In characteristic P, that's not correct. You have to subtract some term here, which depends on the local behavior near each of the points. And the contribution you have to subtract is this thing which I call Swan conductor. So this is a global way of trying to understand what is this Swan conductor in the cases which are relevant to us. Just take the global geometry, compute the genus upstairs, for example, compute the number of points, etc. Using that, you work out something and then you figure out what the corresponding nx must be. And it depends only on the local structure near the point, only on this completion. So there is some, of course, this is not a definition, but there's a property which gives you a feeling for what it's doing. And of course, okay. And characteristic 0, you would just multiply, and saying that it multiplies is another way of writing the so-called Riemann-Hurwitz formula. So That's a pretty standard thing, right? Over C. So, given one of these covering, I can associate a zero cycle, an effective zero cycle, summation nx times x. And somehow I think of this zero cycle as measuring how wildly ramified this original et al. Covering of curves is at the boundary. That's my way of trying to measure, quantify the thing in the case of a covering of curves. This works nicely with curves because I have this local structure and K is algebraically closed here. So there's nothing, the ground field K is not doing anything to this thing here. In higher dimensions, if you looked at divisors and looked at ramification, you could still try to write something, but the picture is going to look something like this. It will look like something like this. With some group G, but where I have a non-trivial extension, and these are not perfect fields even, because these would be function fields of divisors inside your higher dimensional variety. This could even have an inseparable degree. It's not necessarily even so when I write G here, you have to take that with a pinch of salt. Okay. But I can do the following. If I still want to quantify wild ramification of the boundary, I can use curves inside the higher dimensional space to try to understand how bad things might be at the boundary. I can probe the boundary using curves inside the space. That's the idea. So let's start with our x, which is x bar minus d. So I've given myself a compactification. But I now assume that this boundary d is an effective Cartier divisor on the space x bar. So I should have been more careful here. I should have written a mod d there. I want to choose an x bar, which is a normal projective variety. I want to choose an effective Cartier divisor d in this x bar and then delete its support. So I'm allowing d to have multiplicity. D can have coefficients. And then the complement is my x. That's my hypothesis. Okay, I'm considering such x's. So whatever this Cartier divisor is, it contains the singular locus of x bar if x bar was actually single. Okay. Now, if I have this set up geometrically, I can look at maps from a non-singular projective curve to this x bar whose image meets x. I can look at such maps. And anytime I have such a map where the image actually meets x, I can pull back this effective Cartier divisor from the projective variety x bar to the curve C. Functoriality for Cartier divisors. And so I'll get an effective Cartier divisor on the curve. And it will be supported on the inverse image of this D. So that's an effective zero cycle on the curve. And now, if I have an et al. Covering, so this is some, and what are these coefficients? They are more or less like intersection numbers of this curve with that boundary divisor if C was sitting inside x bar. Otherwise, it's a map and you have to take that into account. So now suppose I have a Galois et al. Covering y to x. I'll define it to have wild ramification bounded by D. This is a definition. If we have the following property, you can guess. For any such map from a curve, non-singular projective curve to x bar, consider the pullback morphism C tilde to C, where C tilde is now any component of the normalization of the fiber product. So remember, y bar, if I have y to x and et al. Covering, I have y bar to a corresponding branch covering. C maps to x bar, I can take the fiber product of those two things, I'll get a branch covering of C. But that branch covering of C might be badly singular in various ways, so I have to first normalize it. And then maybe it has components, I have to choose one, but since I assumed everything is Galois, it doesn't matter which component you choose, the Galois group will permute them, so there's no, the geometry is captured by any one of the components. No, nothing. I want exactly not to assume that. I want to allow all possible things to probe. That's the definition. Whether those C's are enough and things, exactly, those kinds of issues are what one has to wrestle with. Let me point out here, I can do this, but okay, maybe I'll come back in a second. And then what I want, the condition I want, the original covering has wild ramification bounded by D if whenever you do this and look at the corresponding covering, branch covering of curves, the Swan conductor of that cover is bounded as an effective zero cycle by the thing I got from this divisor D, fixed divisor D. In other words, I got some integers nx, positive integers nx from the covering C tilde to C. They're restricted by saying they're less than or equal to the chosen numbers mx coming from the geometry of the map from C to x, x bar. Okay, that makes sense? This is a definition. It's a way of trying to bound the ramification. Okay. Given such a pair x bar D, therefore I get some quotient of the étale fundamental group of x, call it pi 1 étale of x bar D, which is the smallest profinite group quotient determined by all such finite Galois curves. Of course, one can ask, is it the Galois group of some Galois category? I don't want to enter into that question. I remember Faulting's grumbling a little bit in Paris when I was saying it. Is there a morphism from, this is the question, natural question, analogous to the Zariski question, Zariski result. Is there a morphism from a curve to x bar, from a non-singular projective curve, such that if I take the induced map on these, restricted fundamental groups of some kind, is it surjective? Can I have a Lefschetz theorem of some kind, a Zariski Lefschetz theorem, for this restricted fundamental group? It's a natural question. We don't know. We are not able to prove.
Same case.
Same case is okay. Same case, there's no wild ramification. So D should be non-zero. That's the point. And there's a weaker way, and we're not able to do it. We don't know the Lefschetz thing. It's a question. It's natural. We neither have a theorem nor a counter. So then say, okay, I can't quite understand pi 1. That's not an unfamiliar situation for complex algebraic geometers also. We don't really understand pi 1 over C in various ways. But what you can sometimes understand instead is look at all its finite dimensional representations. And maybe at least those representations have some decent structure which I can govern in some fashion using the algebraic geometry. So can we manage at least that in this context? That would be a question. So how would we formulate things in terms of L-adic representations? So suppose I have F, an étale QL bar local system of rank R, which corresponds to a continuous representation from pi 1 étale x to GLR QL bar. That's on the open X. Let's also assume, given our compactification and our boundary Cartier divisor D. So I want to not look at arbitrary F's, but only the F's which have something to do with that quotient of pi 1 which I try to write down. So how would I make sense of that with sheaves? I claim for a morphism F from C to X bar, we have again, I claim, a Swan conductor zero cycle associated to the pullback local system on C minus F inverse D. And again, it's coming from the same upper numbering filtration, etc., etc. But now I have a representation of this group. The Swan conductor theory, whatever it is, comes from that. In fact, the way Swan conductor is defined, there's something called the Swan representation in the group algebra, and it's a projective module in the group algebra. And you have to look at the dimension of the space of Hom of something, from that Swan module into. Swan module exists. I'm not sure you can write it down. I guess, right? It's not obviously you can write it down, but it exists. You can prove from character theory and so on. There exists a module, and this existing module, therefore, I can harm it into other things and look at the dimension of the space. And Swan conductor is something to do with that. So it makes sense for anything, is what I'm saying. And since I can make sense of a Swan conductor zero cycle associated to a sheaf, I can ask that its coefficients are bounded by the coefficients coming from geometry. That is, in other words, I'm saying now, maybe I should also say what I did in the earlier case. If I have a map of curves, I can just take the direct image of QL bar on the top curve, that's some sheaf on the base, it has a Swan conductor, And that is the Swan conductor which I used earlier in the Grothendieck-Cog-Schaferowicz business problem. So now for any sheaf, there is a similar way of writing an nx for each boundary point x. Okay? Now, so when I write this, of course, maybe I'm kind of cheating. What I really want to is take this, restrict it to the open set where it's an étale local system, then just think of whatever the boundary behavior is. I'm not worried about this particular extension. That's not the point. Okay? So it then makes sense to say that F has wild ramification, the pullback has wild ramification bounded by the effective zero cycle. And so if this holds for all such maps from curves, I say the sheaf F has wild ramification bounded by D. And that's a meaningful statement. Now I want to consider this collection of such sheaves. SR X bar D, collection of all local systems F of rank R with wild ramification X bar bounded by D. Makes sense to consider this set. So can I prove some kind of finiteness properties or decent boundedness properties for this? That's the problem I want to look at. So of course there's also therefore an associated quotient pi 1 X bar D, but with an extra thing R there, taking into account this rank. And for example, I can ask this. Can I find a morphism from a smooth projective curve C to X bar, which of course intersects the good open set X, such that for any sheaf F in SR, the induced map on fundamental groups, I mean, of course, if I have a sheaf in SR and I have a map from C to X, I can pull the sheaf back to the curve and I'll get a map, I'll get a sheaf also on that curve. And therefore, I'll have a representation of the fundamental group of that thing, which will factor through the representation to the fundamental group of X. So both of those fundamental groups map to GLR, and I can ask, do they have the same image? In other words, do F and its pullback have the same monodromy image? I can ask this question. And it's pretty easy to show that you can find a curve C in X bar, which is just a complete intersection, for one such F. But the problem is the curve will depend on the F. And the whole point of the Lefschetz business, these kinds of questions, is can you find one curve which works for all sheaves? So I can reduce the representation theory of the higher dimensional thing to the representation theory for curves, which we don't understand either, but let's hope it's more tractable. Okay, so this question is a rephrasing of a question in a letter from Deline to Hélène Esnault. It's definitely a rephrasing. Deline, it's a handwritten letter, it's in French, and he has. So this is the way I'm interpreting it. If I've slightly made some mistake, Deline is not responsible for this. Okay.
So just,
yeah.
Could you say a word just for one F?
Yes.
So it constructs
not at the moment. Afterwards, I'll tell you. But it's standard for people who do those, and they know how to do those things. Okay, so let me just say, this is the question, but we don't know the answer of even this restricted question. So this is really the problem we've been trying to study for some time, and we're not even sure if the answer should be yes or no. We're still not convinced clearly in either direction. My belief is actually it's yes, there will be a curve. Hélène is not so sure. Okay. Maybe at the end I'll comment a bit about why I think there's a chance it's correct, but that doesn't mean you can prove it. Okay, so if we can't prove it, what can we prove? Can we prove anything? We can prove a little bit. We can prove some boundedness properties. And we have the following results. So that's what I want to sort of say in the end. So here's one type of statement we can prove. Let's take a finite étale covering y to x, a finite Galois étale covering, which is associated with the representation image of some script f. If you have a script f and take a representation, the image is infinite usually. It's some L-adic Lie group. but therefore it's a pro-finite group. It has finite quotients. Take any one of them of whatever degree. Let y to x be one of them. Let's fix a boundary, think of a fixed boundary component of D. Then the local situation for this covering y to x corresponding to the generic point of D0, that boundary component, is going to look like one of these things. Capital K would be the function field of this component D0. Capital L will be the function field of some component in the covering, in the boundary of the covering. Now, as I commented earlier, these are now function fields. So there's no reason, in fact, that though I put a G, I put G with quotes. This can have an inseparable degree in general. This is not a perfect field. And usually there is an inseparable degree, often for such coverings. And it is related to what's called fierce or very wild or very bad ramification of some kind, where this happens. And Deline, in fact, asked, in the context of those collection of sheaves, do we even know these exponents of this inseparable degrees are bounded in any fashion over the family? And it's not obvious how to guess right away, at least even Deline asked it only as a question, because the way in which we bounded the ramification was by taking curves. And once you pass to curves, you don't see any inseparability at all. The residue field is the same field K. So how are you to probe this non-reduced stuff using only curves? That is somehow something which is, part of one of the things you have to think about. Anyway, so we claim that yes, it's correct. Though the degrees of such coverings are not necessarily bounded, the monodromy image is a positive dimensional L-adic Lie group. You have coverings of arbitrarily high degree. But the inseparable degree along any component is bounded by a constant. In fact, the constant depends only on L, R, the rank, and the coefficient of this D0 and D. It doesn't depend on the geometry at all. That's a little remarkable. It depends only on the multiplicity and the dimension of the representation and the underlying prime L a priori. Okay. At least for me, it's somewhat surprising that there's no dependence on the geometry. Here's another statement. Take any sheaf F in this SR X bar D. Then I claim there's a finite separable branch covering HF from Z to X bar, but I put an F there to emphasize that that data may depend on the sheaf, such that if you pull the sheaf back under this map, it's tamely ramified, at least in codimension 1, on this ZF, and the degree of the map is bounded, independent of the sheaf. Now, again, it's fairly easy to see that given any sheaf, there's in fact an étale covering of X, a finite étale cover, such that the pullback of the sheaf is tamely ramified. The way you do it is like this. You've got a representation. So you've got a group G sitting inside GLR of UL bar, which is the image of our representation. So in fact, this is compact. So you can conjugate it inside GLR of ZL bar, and therefore you can reduce to GLR of FL bar. Now, this is not unique. There are many ways you can conjugate it, but the corresponding semi-simplification is well defined. That you can prove. That you can call that the residual representation associated to the given representation. And this is just coming from the fact that the group is compact, Galois group is compact, so it stabilizes a lattice, many lattices which are stabilized. Now, this is a topological group, and this is also topological with the discrete topology. So the image has to be a finite group. So there's a finite covering where the residual representation gets trivialized. Once you take that finite covering, the new representation is the kernel, and so there is it's a pure L thing. It's an L-adic Lie group with no P part at all. It's a pro-L group. So there's no wild ramification at all. Okay, so it's always possible to trivially construct some covering depending on F. But it depends on the image here. And the cardinality of the image is not bounded over the collection. That's the problem. So what I'm saying, the theorem is, there is a number depending only on the collection, such that I can find a branch covering of that degree, which makes the monodromy tail, makes the sheaf tail. That's the assertion. That's a kind of finiteness property. It's not obvious to start with, and we're saying it's correct. But here, remember, I indicated something which would say there's an étale covering. We are not saying this map is étale on X. We're just saying it's some map to X, some finite degree function field extension. Okay. And the third statement is that our left-edge curve exists if we work with abelian monodromy. That is correct. So at least the rank 1 case, everything is okay. As you imagine, the abelianized left-shade theorem is somehow easier. There's an abelian class field theory, for example. You can use tools coming from that. You don't have to use that language, but the things which go into the proofs give you tools to study this sort of question. So let me comment a bit about those proofs of those statements which I made. Like I said, the first thing on that boundedness or that inseparability was also asked by Deline, and that we managed to prove. And the second statement that the degree which I got, that depends on those same things, R, L, and the multiplicity, but that depends on the geometry as well. That branch covering which I constructed, the degree of the branch covering is bounded, but the actual covering and the ramification and other things depend on the geometry. We're not able to make it independent, and I don't think it's reasonable to expect it to be a universal thing. And 3 was earlier done actually by Kurtz and Saito for the case where X bar is smooth and projective and D is a simple normal crossing divisor. We are able to do the general case. And in fact, like often happens in mathematics, I'm sort of involved with various journals. You see how editorial processes work. There was some technical mistake in one of the things. Since we were trying to generalize this thing, I read the proof very carefully. I found some comment, and then they fixed it. It's fixable. But the referee didn't spot this. Okay. Reassuring, right? Huh? Okay. So let me comment on the proofs. The theorem 1, since I got a universal bound not depending on anything, the input should also be some kind of universal things. And one place is you might ask, what does this R do? I use the R in the form of the theorem of Jordan, that there's a finite, if I have a finite subgroup of GLR FL bar, and the order of that subgroup is relatively prime to the L, the same L, then there's an abelian normal subgroup whose index is independent of anything, and in fact it's the same constant, the Jordan constant, which you would get over the complex number. That's a theorem. In fact, any such representation, because I took a finite group of order prime to L, the representation comes from characteristic 0, and the Jordan theorem OC implies this statement. So I need this. This is where R comes into the... Restricting the rank of the representation allows you to do things like this. Then the second thing is something called the Hasse-Arf theorem in local ramification theory, or these extensions, the upper numbering, all that stuff I was talking about, which says that if you have an abelian ramified extension, the jumps in that so-called upper numbering filtration occur only at integers. That's a theorem which is also important in class field theory, local class field theory. So we use that. And you can imagine using Jordan, we try to get to a situation where we can apply that. That's reasonable. And the last thing is a Bertini theorem of some mathematician of Chinese origin, who was a student of Renault, who is in France. I don't think he does arithmetic geometry anymore, but he wrote 2-3 papers that time after his thesis with Renault. And one of the things is he has a property. He looks at a geometric situation where in characteristic 0, your Bertini theorem would give a non-singular variety, and we know that doesn't work in characteristic P. He proves that wherever in characteristic 0 you would get non-singular, in characteristic P you can get topologically unibranch. This is good enough for certain fundamental group thing. And it takes care somehow, in some situations, of that non-constructive aspect of the business which I had. If you remember, this is not maybe obvious, but let me go back and emphasize this point. Sorry, I got too much nonsense. Here, this thing. I did normalization. This is not a constructive geometric step. It exists, but how am I going to bound it or understand it, right? So what that Zhang's theorem says that for correctly chosen curves, you don't need to bother about it. It's bijective and birational. So for things like the fundamental group and so on, you won't see it at all. That's somehow what, and this sort of phenomenon appears in other places too. I've seen, for example, I remember Lomo lecturing years ago on stuff to do with this stuff and looking at irreducible curves with only cusp type singularities which are homeomorphic to P1 but which are highly singular. They were somehow relevant in his. So and that's a phenomenon. Though you don't have non-singularity, you might sometimes be able to exploit this other thing. Okay? Go back. So what about the second thing, the branch cover or bounded degree, there are more ingredients. You have to use the group theory stuff, which is what happens with the local Galois groups along curves, local isotropic groups, some properties. From that, you do more group theory of some kind. There's some horrible bounds like use factorial of some number, take that, take its factorial, things like that. Some estimates come, but doesn't matter, something, some finite group you construct, or some universal bound. But then you have to do some geometry, and one of the things you do is you use the so-called Harbater-Kautz-Gaber covering. So the idea is that if you have an étale covering, y to gm, so think of this as y bar sitting inside P1, and so you have infinity, let's say here, and then I can look at the local behavior at infinity, the infinity tilde, let's say here. So the local behavior here, if I'm over some field capital K, would correspond to some thing of this kind, depending on what this capital K is, if capital K was a function field. What this Kautz-Gaber stuff does is, it says, if you're only given this thing here, I'll produce some global geometric thing here in some canonical way, which realizes exactly this. So that's somehow a nice construction which we use in our business. So what we are forced to do, what we do is this collection SR X bar D has certain functorial properties as I change the scheme and change the divisor, change the rank, various things. Using these things, you reduce to the case where X is affine space, X bar is projective space, and D is some multiple of the hyperplane at infinity. This you can do only in positive characteristics, by the way. You can't do such reductions in characteristic 0 for representations. But it's like the kind of tricks which go into Hutchinger's business about K pi 1 and characteristic P. Those kinds of tricks allow you to actually reduce to affine space. And then in the case of affine space, I think of the local ring at the generic point of the boundary of the hyperplane at infinity, take that completion, and then do the Kautz-Gaber thing for that. So then I'll get GM over the function field of the hyperplane at infinity. Well, I think of that as birational to projective space. So I spread everything out, and then using that, somehow we're able to do the business. Okay. And the third is just adapting the Kautz-Saito stuff, including the part which had to be fixed. Okay, thank you.
You. Any questions?
You consider exactly the same problems, but not for the full étale fundamental group, but for the group peak quotient. Can you get more?
It's a good question. It might be possible. One has to think. But of course, one of the difficulties, even in the whole finite presentation, is that you can't separate the primes once things are non-abelian, right? So, yeah, but Pro P might not be so
Last
bad. Yeah.
argument.
Right.
So,
Right. Yeah, it might. But then, even in the finite presentation theorem, the P part had a different argument from the L part, as you might imagine. So, but that suggests it may be possible. So, it's a fruitful direction to investigate from. Ah, roughly speaking, my feeling is that the family of coverings which you need to consider should be bounded, or rather, there should be a bounded family of covering such that every sheaf in our collection, pulled back to that some member of that bounded family, is tamely ramified. That would be the first thing. Then, if you only have tame ramification, there are Lefschetz theorems for the tame fundamental group. So, of course, now I don't have one variety, I have a family, but it's finite dimensional. So, there is a reasonable chance that you might get a curve which simultaneously does it for every member of a bounded finite dimensional family. Bounded is important. If you had infinitely many components, I don't know. But really, it's a bounded family in the sense of algebraic geometry. And it seems possible it might be okay. Roughly speaking, if you took an Artin-Schreier cover, so you write a ramified thing of some kind would look like t to the p minus t equals sum, I mean, after adjusting a1 over t plus a2 t squared plus an over t to the n, and you don't have any terms with phi divided by exponent, you have these finitely many parameters, and the Swan conductor is more or less this n in these cases. So you bounded the pole order, you do have parameters, so, and your ground field is algebraically closed, so you don't expect finiteness or finite generation or anything, but may still have finite dimensional parameter families. And in this case, you do have, you can see the parameter. Presumably, my feeling is that might be the picture in there.
Experts? Questions for begin with? Thanks for this.